the top physics at 16. We can ignore earth science, but they're all good. So this would be kind of Midwest severe weather. So it might be some practical things here for us. So the word is may. I think it's important that whenever you see these cumulonimbus clouds, so this is the Earth's surface, this is the top of the troposphere, we call it the tropopause. The troposphere contains most clouds. Some clouds, and I'm going to make a cumulonimbus, a thunderstorm cloud, which is what we're going to be talking about. Some thunderstorm clouds actually penetrate or go into the stratosphere. And this is the troposphere. Okay? So they don't all bring severe weather, okay? But I don't know. They just something about them make me excited and scared at the same time. Okay? So cumulonimbus clouds, which this is cumulonimbus, I guess we shouldn't use the word nimbus, even if it's not precipitating, but I still call it a thunderstorm cloud, whether it's dropping rain or not. They have a lot of energy, and actually the energy is, if I go ahead and put an L for liquid, a G for gas over here, I should put an S for solid. We talked about how water can melt, and then how the liquid water actually evaporates. But within a cloud, when the reason you can see a cloud is because it's at least liquid, if not a solid. And so this going back from a water vapor condensation, okay, that actually releases a lot of heat. So whenever you see a cumulonimbus cloud or a cumulus cloud, or these scary ones, think of actually they are kind of warm. And the warmth they got actually was from the condensation of vapor to liquid. So there we go. So one of the things we know is that warm air rises, and it rises because it's less dense than the air around it. So if I put the word warm here, this is warm relative to the surroundings, so that actually makes it want to go up. And this kind of upward motion is what we call the instability associated with a cumulonimbus cloud. We're going to talk about cells. If you think of the word cells, you might think of something circular or square, but you think of it kind of unitized. So as it turns out, even though sometimes we say there's a thunderstorm system coming by, well, actually there's individual thunderstorm cells that are coming by. We'll kind of talk about that. So each cute little cell goes through these three stages. First is the cumulus stage, and if you think cumulus, you run into that word meaning a fluffy cloud. First is the cumulus, and then it's the mature stage. You think mature, you think, oh, that's scary. And that is scary. So I have a slide that says mature stage is when you're going to get your drenching rain and your lightning and maybe even your hail and your tornadoes. And then we go ahead and end up, the third one is called the dissipating stage. So cumulus, mature, and dissipating stages. And all thunderstorm cells, whether they're just by themselves or kind of united in a group, we call a multi-cell thunderstorm system, they all go through these same stages. So here's the cumulus stage. Remember, anytime you see white fluffy cloud, think this, okay? Think liquid or solid, okay? Because if it's a gas, you can't see it. So the word is cool. So one of the things we know about chunks of air, I tried to kind of touch on this, is that a while back, is that if a chunk of air rises, it's going to get bigger. And that getting bigger actually is work, and the work is funded by the energy of the chunk. So it's like it has to get cooler if it gets bigger. And if it goes up, it has to get bigger. So getting cooler is one way we know to go ahead and make getting cooler, we know we can get condensation, and that's what's happening with the cloud. So as it goes up, though, can you see these little red arrows? I like these figures. As it goes up, it's actually kind of creating a little waft. It's called an updraft, a gentle updraft. Okay? I touched on this LCL. The L stands for lifting, C stands for condensation, the other L stands for level or elevation. So lifting, condensation, level. That's basically why most bottoms of clouds are flat, because they had to kind of rise and expand and cool right to what we call the dew point temperature, the temperature which you could go ahead and condense water. Okay. If you're in the beginning stages, and I know you guys have seen this, and you might have to kind of pull on your springtime and summertime, when you think of thunderstorms kind of forming, is when the clouds first starts to be pushing up like that, it's nice and crisp, the edges are nice and crisp, versus kind of diffuse or fuzzy. All right, so the mature stage, notice we have, the word is intense, mature, intense. So notice that we have the red going up, that's just air moving up, but now we have the blue downdraft. So we have air going up and air going down. And I think this will work. If you've ever taken a balloon and put it on your head and gone like this, okay, you basically can transfer electrons, I can't remember which way to which, but basically you make static electricity, okay? So kind of along those lines, within this now mature thunderstorm, we have an updraft and a downdraft. That rubbing actually can create some of this electricity that's going to give us our lightning. So updraft and downdraft. Now the downdraft actually is what we say associated, or I think of created as the raindrops fall. Okay, the raindrops fall, they create a wind going down. Okay, so we have the updraft and we have the downdraft. Now I'm going to look at it. We're going to look at a better picture, better figure of a mature thunderstorm cell. But there's this thing called an anvil. If you think of an anvil, it's like, well, you know, it's kind of flat on top, and it's something you can kind of pound on with metal. But that top part up there is called the anvil. And the anvil, actually, think of the anvil. I'll go back to this kind of crude drawing. If I was to draw this better, I might kind of flatten it out more here. Okay, so think of the anvil as created as it actually leaves the troposphere and tries to go in the stratosphere. It's flattened out. Okay, what else we got? Okay, so this isn't a stage, but this is talking about a phenomenon called hail. Now, remember we talked about different types of precipitation. We talked about rain and snow. We talked about sleet and freezing rain, okay? That's totally, I told you at the time, that's totally different than hail, okay? You wouldn't expect sleet and freezing rain to come from a cumulonimbus cloud. You may get hail from a cumulonimbus cloud. What they have in common is they're cool little pellets, okay? Maybe not so little. Some of you guys might have had some hail stories to share. They're pretty big. So what's happening, and the word is updraft. What's happening is you can see the red updraft, the blue downdraft, and kind of the purple path of the stone, the hailstone. Okay? So this introduces something that's important. If you're, let's see, I don't fly much, but if you fly, well, a little bit, if you fly, they always put like a solution on the wings so that, how do I say this? Solution on the wings so that the wings don't freeze. Okay, here's the deal. As a plane is pushing through clouds, okay, or, yeah, that would be right, clouds, actually a lot of that liquid is what we call supercooled water. Well, there actually are super things in physical science. So supercooled water, like the slide says, is water that is liquid at a temperature way colder than it should be. So it's what we say kind of unstable in that super condition. So if you didn't de-ice your planes, put that solution on there, as it's flying through that super cold water, basically you just coat into just it'd be kind of like freezing rain. Freeze on contact. Okay, so anyway. So the super cooled water is just itching to go ahead and solidify. So anyway, picture that sort of scenario. You can see kind of the purple going up and down and up and down. Okay, so it'll go up and down a few times. Of course, as it goes down, it's maybe hoping to fall, but the reason it would go up is because the updraft takes it up. The reason it would come down is because it gets heavy. It goes up because the updraft, it goes down because it's heavy. At some point, it gets too heavy, the updraft can't keep it up, okay, and it comes down. So this is kind of I think the word is even stronger. Then the word is layered. So these actually are hailstones, and you can see that They kind of have a scent, they look like an onion. They have the middle part, which formed first, and then as it did one cycle, it got another layer. One cycle, it got another layer. So big old hailstones, you can see the path that they've taken. Okay. So the word is strength there. Sometimes weather folks, meteorologists, people trying to tell you what the conditions are like in severe weather like this in the spring or the fall, associated with cumulonimbus or thunderstorms, they will talk about updrafts. So the stronger the updraft, kind of the scenario is painting, the more you can go ahead and have that hailstone cycle up and down, and get larger and larger and larger. So that's bad, sad face. I didn't include it in, I think it's interesting, I didn't have time to include it, but there's actually been folks that have tried to modify the weather, interfere with the weather, and to a certain extent, you can maybe try to seed this or make it so they don't grow so big. So, weather modification. All right. So we have cumulus stage, mature stage, and then we have dissipating stage. So if I were to ask you what the big difference between this figure and the previous figure are, you might notice that you don't see the red updraft anymore, so dissipating. Now the updraft is important because it's bringing in the raw moisture. The updraft is important because it's bringing in more water vapor that can liquefy and create energy, okay? No updraft. It's beginning and the end. Okay, so the downdraft has completely dominated the updraft. See a little bit of an updraft up there. Kind of still seeing an amplifier. And again, you've probably experienced these three stages. You know, the whole, oh my gosh, the cumulus stage, and the oh my gosh, the mature stage, no, the dissipating stage. So the precipitation is different here. It's kind of nice, a little lighter. Okay, so yeah, without the updraft, the moisture source is cut off. Okay. So, I do have a few videos. This is one where I at least want to start it. Okay. So, the word is tilted. So you've probably seen these before. I wrote this one. This is called majestic, actually. This is majestic. Tilted means it's slanted. The slanted ones are the ones you gotta watch out for. I have a picture kind of showing you that. Okay. So the slanted ones actually are able to go ahead and last longer because they've gotten the updraft and the downdraft away from each other. This one, this figure kind of emphasizes the anvil, and actually the direction of the big anvil, sometimes there's a back anvil too, but the long anvil, it's pointing you the direction to where the storm is going. Okay. So here's one for you. If you're looking at a thunderstorm in the distance and you can see the lightning, and haven't you ever like looked at the base of the cloud and you're like, man, I can kind of see the haze, the fuzz. I know that's precipitation. Sometimes then you had felt like a wind in front of that. That's called a gust front. And if we kind of track back where that gust front is coming from, here's the gust front. Here's you sitting on your porch. It's not raining yet, but you're feeling that. Like, oh man, we better go in. So what's happening is actually this downdraft, I said, is kind of creating wind as the precipitation, the little cute little rain droplets fall. They create a wind going down, and that wind splashes in both directions. And one of them is the direction to which the cell is headed. So that's a gust front. I want to show you, see this one right here? The video I want to show you kind of talks about that, and I'll go ahead and call that is inflow. The warm, moist air, this right here, this is called inflow. So you have a gust front coming this way, and you have an inflow going that way. So the video I'm just going to show you takes a look at that. Okay, so that's tomorrow. Feature, so we have the anvil, we have the updraft and the downdraft, we have the gust front, and this is a cute little shelf cloud. Kind of, again, it's kind of a precursor to the direction that the storm is going. So this right here, where it says developing cell, Actually, that in this case is our shelf cloud. Oops, is that going to go right here? Looks like a shelf, doesn't it? Okay. All right. So we have our normal thunderstorm cells, which are totally exciting for me. Okay, our normal thunderstorm cells, and then we have our supercells. And you've probably heard weather people get all excited about, oh my gosh, it's not just a regular thunderstorm cell. It's going to go through cumulus, mature, dissipating, but it's a supercell that's going to go through cumulus, mature, dissipating. Okay, so these actually are more likely to bring severe weather. And it's interesting because there's criteria. If our National Weather Service sees an ordinary thunderstorm cell, they're not going to put out an alert. But severe thunderstorms, actually, they have to have one of three criteria. One is have hail, a certain diameter. That says that initiates that call. Another one is spawn tornadoes. And, oh, the other one is wind. Notice what I didn't say is lightning. So I'm here to tell you that lightning takes a lot of lives that hopefully that actually probably shouldn't. So just ordinary thunderstorms have lightning, and you will not get an alert for that. Okay. So supercells. This is looking at a supercell from I don't know if that was some satellite image, something that's beyond, something that has to be up here, looking down. So you're looking at the tops. Okay, and we can actually look at the tops in terms of their temperatures to get a sense for the instability in those cells. So we have two cells here. Like this says, they're big supercell thunderstorms, supercells. Okay, supercells are generally large and they last a lot longer than the ordinary thunderstorms. So this is the diagram of a supercell, and it has some similarity to an ordinary thunderstorm cell. One of the things that's different is this mesocyclone you see in the middle of it. So this is a supercell. Ordinary cells will not have this. The word cyclone might say, cyclone, rotation, cyclone, tornado, and you're right. Actually, this mesocyclone is what may or may not be the region that a tornado drops out of. Okay, so the thing about a mesocyclone, the word is wrap and intensifies. The thing about that little churning is that it takes our updraft that is bringing in more moist air and our downdraft created by the precipitation, and it basically makes them kind of twisted. Can you see where this one is slanted? Okay, I talked about tilted a few slides ago. The tilted nature of a thunderstorm cell should make you afraid. For a few reasons. One is that it can last longer and become more intense. And the other thing is, if it's tilted, that means it's tilted because we have very strong upper level winds. And those strong upper level winds is one of the couple ingredients to give us tornadoes. So, in case there wasn't enough for you to be worried about. Yeah, so supercells, people get all excited about supercells. So listen to meteorologists when they tell you that. This is actually a photograph of, you can see the cumulonimbus cloud up here, this tornado dropping from the mesocyclone. And a lot of times tornadoes will drop from what's called a wall cloud. Wall clouds are kind of like, they're kind of squarish looking clouds. I'm thinking it might be here. A wall cloud, they will tell you if you're a spotter trying to find tornadoes, that look for what we say rotation in the wall cloud, and the tornado will drop out of that. All right, so it's quite possible that the conditions to give you one thunderstorm can give you multiple thunderstorms. So they kind of gang together. Okay. So if you have a multi-cell thunderstorm system, it can last a long time and cover a large area. There's two types of situations where multiple cells get together. Now these could be multiple normal thunderstorm cells or multiple, heaven forbid, supercells. Lots of love there. So this one, you probably heard this one before. This is called a squall line or this is not called, but this is showing you a squall line of thunderstorms. Now, we've talked about weather fronts. Squall lines usually come from cold air pushing into warm air. That cold air is really dense. It acts like a steam shovel, and it lifts up. And if this, we got moisture here. There you go. A whole row. It's a row of thunderstorms. Then there's this one. It's the blobby one, and the word there is MCC. So this is the other sort of system where you can have multiple thunderstorms kind of doing their thing. If you look at kind of scale here, let's see, here's Iowa, okay, and you can kind of see this is about the size of a state here. That angry looking red thing, actually think of that as a lot of little thunderstorm cells that are going to live their lives and die, and then more thunderstorm cells behind them. This is what we call a mesoscale convective complex. Okay, so these are, I think, like if you get hit in the middle of the night, just a blob of thunderstorms, like they just don't stop. Oh, it's kind of nice to go to sleep too. This is probably what's going on. Right. So let's talk lightning. We're not going to talk as much about how lightning forms, although I kind of gave you an idea about the whole, take a balloon, put it on your head. That's kind of like what we have when we have the updraft and the downdraft going on. Basically, you have to get some charged particles up there, and that's the beginnings of lightning. But I want to focus on, there's two types of lightning. There is this lightning, sheet lightning, not to be confused with heat lightning, which I have a slide on here. Okay. And sheet lightning is the kind you don't have to be afraid of. Okay, sheet lightning, okay, that's the cloud-to-cloud lightning. So it's between two different clouds or even within the same cloud. All you got to do is get a charge separation. And so the electrons flow from where it's positive, where it's negative. Sheet lightning is beautiful, though. And then this is the scary lightning. So most lightning couldn't hurt you, sheet lightning, but 20%, so that's 80. 20% of lightning is this cloud to ground lightning, okay? So the word is tall there. So here's the deal, and I've seen pictures like people, but anyway, if you are out and about and you see a thunderstorm cell over there, storm cell over there, and if your hair starts to stand up, then you are probably a relatively tall object for this to begin, we'll call it a charge induction on you. You are reacting to that thunderstorm. So anyway, I'm just saying. They say, and I don't have a slide for safety, I have one for tornadoes, but not for this, but they say get on the balls of your feet and crouch down and stay away from tall objects and cows. No, I don't know about cows. Okay, but so anyway, but I have, let's see, I think this is where I'm going to go out here. I have a little video to show you. It's short. I think he says a bad word, so I apologize in advance. I think that's. So here's one for you. You probably already know this, right? Growing up, you might have been taught that the longer the delay between when you see the lightning and you hear the thunder, the longer the delay, it means that that system is farther away. If you've ever heard that before. And the reason is because lightning, the visible lightning, that light travels basically at the speed of light, a little bit slower than the speed of light. So it travels a lot faster than sound does. Sound is a lot slower to get here. So that's the delay. So here's a general rule. I don't know if this is what the word is miles there. So there's different kind of formulas, but if you count like seconds, like 1001. So here you see here, crack, 1001, 1002. Wait a minute, no, I did that wrong. You see it. So you see it first, 1001, 1002, you get to 10, and then you go. So that delay when you saw it and you hear it, 10 seconds, you take 10 divided by 5, that's 2, so it's 2 miles away. So if you basically see it like we did in that video and hear it at the same time, that means it's right on top of you. Congratulations. Okay. Another thing, and I kind of mentioned the whole hair charge and all that. If you can hear thunder, I think this is right. If you can hear thunder, then actually you are a potential lightning bolt target. Because actually lightning can reach that far in advance. So the old adage, they say, you know, stay indoors until so long till after you hear no more thunder. That's okay. So sheet lightning and heat lightning. Now they're kind of related, but they're different. So heat lightning, the word is far away. Heat lightning, I think it got its name because sometimes in summertime it's like nice, it's hot, too hot. You're just enjoying the evening, too hot to be inside. So you're like looking in the distance and maybe you have like a squall line of thunderstorms or just a thunderstorm. Like, oh man, that's cool. So you're enjoying the picture show, but you don't hear anything. I don't know if you guys can relate to that. My dad I used to sit out and watch those things. So anyway, it still is thundering. It still has the audible portion, but that sound can't, it gets less and less and less and less, and sound doesn't make it to you like the light does. So that's heat lightning. Then there's a couple different types of thunder sounds, qualities, I guess you call them. So the first one is like we saw in the video, okay, and then there's the rolling one, okay? I like that one too. Now, in order to get the rolling one, you have to have some sort of, I think it has to be kind of in the distance, and you have to have some objects. Maybe they're hills, maybe they're buildings, but it kind of it kind of rumbles. Okay, and the quick one, and then kind of the rolling thunder. All right, let's talk tornadoes. So I think I'm going to kind of finish up my slides and see. Hopefully, we have time to go back and look at some footage of tornadoes. That's where that link would take us. But tornadoes, the only type of cloud you're going to get a tornado from is a cumulonimbus cloud in its mature state, where you have an updraft, a downdraft, and a mesocyclone. Blah, blah, blah. Okay. So what a tornado is it is a air moving up, and actually it's got a picture of the tornado is right in the eye of the tornado. You have a central low pressure. Now there are definitely some similarities between tornadoes and hurricanes. There are a lot of difference between tornadoes and hurricanes. Hurricanes last a lot longer. Tornadoes are kind of hard to find, but they both have this kind of this eye thing going on, central low pressure. So the eye of a tornado will be where you have your low, and there's been all sorts of, maybe you are already aware of scientists trying to understand tornadoes. And if you watch the movie Twister, you know, that was all about folks chasing tornadoes and trying to understand them. She had her, was it her aunt? Maybe she lost father for a tornado, but then her aunt May, so she can try and save her aunt May. But what I started to say is they have like had interceptor programs where they're trying to put like a tank sort of thing, have the tornado go over the tank and gather data while it goes over the tank. And they've also done, just like Twister, where they've sent like little probes up into the tornado, and those little probes then actually send back real-life data that can be helpful. Tornadoes, we have big ones, we have little ones. They can vary, they can be just a couple feet long to up a half a mile long. They come with different names, like this would be kind of like a wedge tornado. Okay, this would be a rope tornado, kind of different names. They last different lengths of time, minutes up to several hours. Okay. How fast they rotate actually then is balled up in kind of the destruction they create, which actually then is how we assign them. I have the F1, F2, F3, F4, F5 is the worst. Okay. So the word is after here. That's one of the differences between tornadoes and hurricanes is we can only categorize them on the Fujita scale, the F scale, after the fact. And hurricanes, they're categorized as they go along. Tornado extremes. Okay, down here actually, the number is 59 people. So what you're looking at, these little pictures, this is an aerial view on the right and kind of a surface view on the left. Tornadoes, just like thunderstorm cells, can kind of come in clusters. You figure if you have a cluster of thunderstorm cells, and if they are super cells, which may or may not all give us tornadoes, we would call that a tornado outbreak. I have some numbers up here. The second line, the deadliest tornado was in 1925 and 695 people were killed. But you figure in 1925, one of the things we've come a long way is our warning system. So the next line, so the biggest day-long outbreak was 147 tornadoes. Just the other day, 1974. The widest tornado, 2.5 miles. The fastest moving tornado, 302 miles per hour. And the longest tornado to transport anything, and it was a personal check, was 223 miles. Like, dude, are you serious? No relocation of material by a tornado. Anyway. So this you can kind of see from left to right. Here over on the right, this would be kind of our finished product. You see this red thing is the mesoscale the mesocyclone, in the cumulonimbus cloud that may give us a tornado. But over here on the left is like, well, how might they form? And this is kind of showing you kind of a rolling, like you roll a pencil of air, because as you go up in elevation, the winds get stronger in general. So kind of rolling air, and then we have an updraft to kind of prop it up. So I don't know. Oh, the word is difficult. And kind of related, the next word is triggers. So the science behind tornadoes, one of the problems is they don't last very long and they're hard to anticipate where they'll be. The word is updrafts and winds. So I mentioned the whole tilted. This one isn't so scary because to me it's more majestic instead of tilted. But the whole tilted cumulonimbus cloud should give you reason to pause, okay? Because that's an ingredient for tornadoes. 1 in 100. So say you get 100 thunderstorm cells, maybe one of them will give you a tornado. And the word is hail. So if you've watched some of these storm chaser videos, they are fascinating. They're braver people than I am. You can see that a lot of times as they are chasing maybe a supercell that they're hoping that will drop a tornado for them, they'll run into some hail ahead of time. So this is another look at a mature thunderstorm. This is specific. I'm thinking this might be a supercell. But here we have some things we've talked about. The anvil. Okay, actually there's a front anvil, should be longer than the back anvil. The front anvil will tell you the direction it's moving. I haven't mentioned it yet, but I drew it, and it was on the previous figure too. This right here that's in the stratosphere should be nice, and it looks like cauliflower. Nice and just makes you want to chomp into it. So that's actually what we call the overshooting top. The thing that's overshot is the troposphere. Oh, this is penetrating top. I'll put the word overshooting because I think my other slide has overshooting. So penetrating or overshooting. I guess penetrating is pretty, or. What else we got? Oh, here's one for you. You might have seen, there's 10 cloud types. There's this other type of cloud that's not one we talked about. It's called a mantis cloud. And it's kind of like a drippy sort of pouchy, kind of looks like really soft cotton balls. And you can see them underneath the anvil sometimes. And I've seen them other times too. Kind of weird. So what else we have down here? We have this would be our downdraft. I know it's our downdraft because we have the precipitation here. We have an updraft here. And anyway, so I mentioned wall cloud, and this is a figure to try to show you what I was trying to describe. Of course, we see this little thing is the tornado, and it's dropping down from the wall cloud. So what I described is kind of a cylindrical, kind of less of a pokey outy thing. kind of that, and they kind of look for rotation there. Kind of distracting sometimes when you're driving down the road and you're like, oh man, that looks nasty. So then you start to kind of look at the features of the thunderstorm, you're like, look for this and look for that. Okay, so categorizing a storm, categorizing a tornado, a twister, comes after the fact based upon the damage. Instead of the Fujita scale, now it's the EF or Enhanced Fujita scale. So F stands for Fujita. And the scale to classify hurricanes, which we're not going to have time to talk about, is a different scale. So actually it goes from 0 to 5, not just 1 to 5. And you can see the columns, how fast the wind was moving, in both units of kilometers per hour and miles per hour. And then over here, though, this last column, the damage, is what they're going to be looking at to kind of backtrack to how fast it was, to backtrack to assign it an EF number. So I have a figure coming up to kind of emphasize what this is, but 69, almost 70% are wimpy tornadoes. 70% of tornadoes will basically, you won't have hardly anybody killed. That's a lot. 70% of tornadoes are Fujita 0 to 1. 30% then, well, plus 30. The math there, less than 2%. Okay, so about 30% are middle, okay, and you do have some people killed, but only 2% are your EFs, 4s, and 5s. And of that 2% is when 70% of people are killed. Okay, so there you go. Do you see Tornado Alley? So this is color coded. So the more closer it is to red, then the more the caption is the number of tornadoes per year. So yeah, you can kind of see this range from Texas and watch this. I learned this today. I'm bad with my states. That's why I gave you guys a thing the other day. Are we there? Okay, good. So some people would say like Des Moines and stuff like that is, but I don't know. It's part of the purple, which is more than. This is really good. The reason that there are some hot spots has to do with the fact that some places have better ingredients for tornadoes, if you want to look at it better. This is what I told you a minute ago about the weak, the moderate, and the very strong tornadoes. So the first bar is how many there are, and the second bar is how many people die. So here we have a lot of them, not many people die. We go over here, we don't have very many of them, and a lot of people die. So this I think is kind of interesting. The little dots are like represent kind of a certain number of tornadoes. So this is worldwide speaking. I'm thinking God doesn't like us very much. You know what I'm saying? I mean, tornado-wise, you know, we definitely get hit. And it has to do with, I've heard it described that we have kind of these north-south running mountain ranges on either ones of our coasts. So tornado safety, get indoors if possible. The next word is interior, so you may have heard this before. And it's good to think ahead if you're if you know there's severe weather or if you're in a place a lot of times. Okay, think ahead to an interior room, lowest level possible. Cover yourself, and I've kind of had this conversation with my mom, who lives at home alone. Cover yourself, if possible, in case there's flying debris. Now, here's one question. Actually, my mom lives in a double wide, so if you are in a mobile home, you're supposed to go outside. Seek shelter in a fixed building or outside. I don't know if I'm going to convince you of that. If you're driving a vehicle, get off the road, get out of your vehicle, and seek shelter. If you're unable to get to a shelter, you've got to be outside, get to as low as possible. Okay. A really common, you've seen this too, mistake people make is to hide under like overpasses, you know, yeah. So it's tempting because then you're out of the precipitation, but you're setting yourself up for, for a problem with flying debris or the overpass falls on your head. Okay, I'm going to finish up kind of talking a little bit about tools that we can track tornadoes. This isn't just tracking tornadoes. This is tracking, I guess Doppler radar tracks mostly tornadoes. We talked about Doppler before, and the word is moving here. And the Doppler effect, I think we talked about this in astronomy. Basically, if something's moving towards you, you're going to get what we call blue shift. If it's moving away from you, you're going to get a red shift. So what folks can then do, the word is shortened. What folks can do, meteorologists can do, and the word is longer, is look for rotation. So sometimes meteorologists will say, oh my gosh, there's rotation. And the way they got the rotation was this Doppler radar to understand it, that there's rotation. So the word is red. Okay, so this is kind of showing you, this is showing you the Doppler image. This one up here, you see it says tornado, it's marked, and can you see the red and the green? That's rotation right here. Okay, so the fact that they have something moving toward and something moving away in a small area means that they have rotation. The word is hook echo. Okay, so switching gears, this one is Doppler. Okay, so you kind of see we call that a tornado vortex signature. It's a signature of a tornado right there. This one is just regular precip, and this is showing you kind of lots of precip where it's red and light precip where it's green. But the shape of it's what we call a hook, kind of a hook pattern. And in that case, if you have a hook echo, a hook kind of pattern of precipitation, you're going to be looking right here in kind of the little hook of the hook, okay, for your possible tornadoes. And so these actually are complementary. These are showing you the same. This is Doppler, this is regular. So the presence of a hook actually, and you'll hear weather folks talking about supercells, and they'll be talking about, oh, we see the precipitation in the form of a hook. You're like, oh man, that can't be good. Or if you're excited about that sort of thing, okay? So the top thing up there, the top thing being this one right here, this guy right here, that is your tornado vortex signature that kind of shows you the rotation. Hook echo right here.
On the study guide, you have bow echo. Is that what the hook is? The same thing?
No. The bow echo, yeah, I'm probably going to have to take a look at that. The bow echo was, remember when I had a squall line? This is like my map of the United States. And here's Canada up here. And we kind of had like all of these thunderstorm cells. Okay, so it's something different. This is kind of the bow. Yeah, I'm going to have to double check.
Okay.
So it's different. But that bow echo is an indication of kind of a squall line with thunderstorms coming through.
So do we need to know it or not?
That'd be extra credit. It kind of snuck on there. So next to bow echo, the extra credit on the test, but bow echo is this right here.
What's the
And then the gist of it, what's the gist of it? It's a bow echo means it's another indication of basically you have upper elevation, fast wind kind of making this squall line do this. It's from a squall line. Oh goodness, I can't spell squall. Squall line of thunderstorms. Each one of those circles is a thunderstorm. Squall line. S-Q-U-A-L-L. Squall line of thunderstorms. Very good. Oh, the word is, I don't know if you need the words here. Vortex signature. That probably would. And the last one was just okay. And then this one just kind of summarizes again what we just talked about. These are complementary. So this is the tornado vortex signature, the red and green. This is the hook echo. Kind of they've drawn a black line to kind of show you the hook where the bad weather could be. This is another day. This is the regular radar showing you precipitation, the shape of the hook, and this is showing you the tornado vortex. Thanks for bringing it. That would be extra credit. Okay. All right. And I'm in my office usually, I'll be there by